So far we have discussed how the sampling process takes place to convert the continuous time signals into discrete time sequences. We discussed the Z transforms and how to convert sequences into its frequency representation in Z transform. And also we discussed the meaning of Z minus 1, or what Z represents, because basically Z minus 1 represents a delay of one interval, that kind of stuff. We also look at the stability issues. If you have discrete time transfer function and you find 0 in the poles, and you want the poles to be negative, you don't want the poles to be negative, you want the poles to have a magnitude that's less than 1. Okay, so sometimes I get muddled up myself. For continuous time, you want the poles to be negative. For the discrete time, you want the poles to have a magnitude less than 1. Okay, for the system to be stable. And in this part, I'm going to go through the design process and to look at how we can actually convert the controller we design continuous time into forms that can be implemented in digital systems. Okay. Now, to do that, there are two important issues to discuss. One is the clock. What is a sampling interval? Okay. What is the best sampling interval for our design in a particular closed loop system? That's the first issue. The second issue is how to convert. What is the best way to convert the continuous time controller into digital form? Okay, so there are two issues here I'm going to discuss for this part. Now, I'm going to start with by giving you an example here. Now, I have three different sinusoidal signals here in continuous time. The red one has a frequency of 0.5 Hertz. The blue one has a frequency of 1.5. The green one has a frequency of 2.5 Hertz. Now they are shown in this graph. Okay, so the time scale is from 0 to 1. This is their amplitude. So the amplitude of the sine waves vary with time. Now if I select a sample interval of 0.5 seconds, that means for every half a second, I'm going to take a value, or the computer will take a value, convert that into digital form. So at 0 time, at t equal to 0, it takes value. For red, it's 0. For the blue, it's 0. For the green, it is also 0. Then the computer will go away to other things, come back at 0.5 seconds, which is right in the middle of that graph. 0.5 seconds, if I go top there, red is 1, blue is 1, the green is also 1. So I have 1 for my second value for all three sequences. And then computer will go away, come back in another half a second. That's at there, t equals to 1. If I go up there, the red is 0, the blue is 0, the green is 1. I can continue the process, and I will find a sequence for the F1, which is 0, 1, 0, minus 1, 0. I can continue to find the sequence for F2, which is 0, 1, 0, minus 1, 0. I can find the sequence for the third signal, that's 0, 1, 0, minus 1, 0. So you can see here. In time domain, we have three completely different signals. But what computer gets will be the same from the three. if my interval is 0.5 seconds. This problem, this kind of problem is known as aliency problem, due to the fact our sampling interval is not selected properly. Okay, we have not got a good enough sampling interval. Okay, in this case, the computer will treat the second signal as if it dealt with the first signal. The computer will treat the third one the same way as the first one. So basically, it treats the signals or sequences with high frequency as if they were low frequency. So you get mixed up. If I have two sequences mixed together, F1 and F2, or F1 and F3, then they all both be mixed up as if they were all this signal. Okay, so this is one of the problems with digital control that you have to watch out for. That is to select the right sampling interval to avoid this aliency problem. Okay, the only solution here, there's no other way. The only solution here is actually to try to find much smaller sampling interval so that you don't cause this problem. Okay, so we have some guidelines, okay, as well. The other thing, if you are about the sampling interval too small, is this. When you go back, so computer does all the calculations and come back to the plant using D2A to convert these dots, these values into analog signals. Because we have to use the zero holder, remember, because computers is busy with other things in between, it doesn't really give you an update on the values. So for this sine wave, it will give you a value here and then keep that value constant. So as far as the object is concerned, as far as your plant is concerned, the value between here and there is flat 0. And then computer will come back and give you an update. And then after that point, it will keep that value at constant. So instead of a sine wave, you get this. It's a problem we already discovered a little bit, but the point I'm trying to make here is not about that steps. It's about the average of that. You can see if I draw a sketched average of that black line, there's a delay between the red and black line. Delay in closed-loop system means phase lag. Phase lag is bad for us, okay, because it compromises the phase margin, and therefore compromises the stability. Now, in this particular case, if you look at it for one cycle, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is the 10th, that will be beginning of the next cycle. For one sinusoidal cycle, I take 9 samples. Okay, 9 samples. One cycle is 360 degrees. 360 degrees divided by 9 is 360 divided by 9 is 40 degrees. And then if you look at it closely, the average, if I do an average of the black line, that's about half an interval. So there's a delay of half interval. Okay. 9 samples, one interval will give you 40 degrees, but half an interval will give 20 degrees. So you get, because this sampling zero order hold business, you get a delay of 20 degrees. Negative 20 degrees, that means you lose 20 degrees in your phase margin. Now, in our design, we did try to find a design system that will give us a good phase margin. Now, just because we introduce this digital system and you lose 20 here, that is a lot, in feedback control. So we need to be very careful with the selection of the sequence. There are two issues here. Okay, one is the annuency, the other one is the delay. Okay. So there's a theory says that if a sine wave of particular frequency is sampled and reconstructed mathematically from its sampling, then your sampling, what it says, this theory says your sampling frequency must be no less than twice of the frequency of the original signal. So that means if the sine wave, the frequency of sine wave is f, then your sampling frequency must be at least 2f. Okay, that's the limit for sampling. That's the minimum requirement for sampling. But in practice, because we have delay issues as well, so in control systems, we tend to use at least 10 to 100 times. Signal processing is a distortion that matters rather than the delay, so the requirement is slightly less. So for signal processing, it's about 5 to 20 times, but for our feedback control, we are talking about 10 to 100 times of the maximum frequency you have to deal with. Okay, so if your controller or control system has a bandwidth of particular frequency, or the quarter frequency of a particular value, then the sampling frequency you choose is 10 to 100 times, perhaps towards 100 times rather than towards 10. Okay, and then you can, from the sampling frequency inverse of that, you'll get your sampling interval. Okay, so you would really need a much smaller sampling interval than the theory will allow you. Okay, so that's practice for you. So remember that 10 to 100 times of the highest frequency a control system has to deal with. And we also safeguard that. Say, for example, we choose a particular sampling frequency because we know the maximum frequency range the controller has to deal with. But there are other signals may creep in, like noises in a system, which is not something that you can expect or you can predict. So we use an extra measure called anti-aliasing filters to remove any frequencies higher than what you expect of the signals to deal with. So if you choose, for example, a particular sampling frequency, you will need to design a low-pass filter to get rid of the any signals with a frequency higher than half of the sampling frequency. Okay, it is typically constructed with an analog circuit and placed before the A to D converter, and this will give you a typical filter that people use in their implementation. It's basically a resistor and capacitor. The transfer function of that is 1 over RCS plus 1. And RC value, you choose IC value to have an inverse of the frequency, 1 over omega. Omega is what? Is a half of your sampling frequency. Okay? So you choose sampling frequency to give you a reasonable sampling interval, and you take half of that, and you inverse the value. That's the value you should use to design your anti-aliasing filter. Just get rid of the noises problem, so that computers don't take in these extra signals and treat them as normal low frequency values. Okay, that's called anti-aliasing. Aliasing is a problem where the high frequency get mixed up with low frequency signals because of sampling process. Okay. So that's how you determine the sampling interval. from sampling frequencies, and the guideline in practical terms is towards 100 times. Okay, between 10 to 100, but towards 100 times of the maximum frequency you have to deal with in the system. Okay, so you choose that sampling frequency, you half that to design your filter. And then you inverse the frequency, sampling frequency, to give you the sampling interval. Okay, so the first thing, this is very practical. Okay, it's not something that coming out as strict calculations. It's really sort of something that people try in practice and find these values will give you a reasonable response or reasonable performance. Okay, so every system will be different because every system will have to deal with different frequency range. Okay, in general, the higher frequency, the faster response you get out of the system. Okay, but that also means you need faster computers. Okay, so selection of the sampling frequency and sampling interval is one of the early decisions you have to make when you design digital systems. Now, once you decide that, then we are ready to convert the controller in continuous time into discrete form. Okay. Now, there are many methods of doing the conversion. Now, if you think about the controller in continuous time, it's basically Ks equals to a transfer function. In the transfer function, the only variable you have is S. One of the methods to convert from continuous to digital is use this equation number 1 here. So S equals to 1 minus Z to the power minus 1 divided by the sampling interval. Okay, this is an approximation between S and Z. Okay, the meaning of that is, we are actually going through the mathematical approval for this, but what is essential is to say, right, because now the dotted line here is a continuous signal. If I look at that particular point, I draw a slope here. This is the rate of change at that particular point for the dotted line in continuous time. But for digital systems, we don't have any values in between, because the only value I have here, the only value here I have is there. So I work out the slope between these 2 points and approximate that to the blue line there in continuous time. If you, as long as your t is small enough, this line is very close to the blue line. Okay, or the slope of the both will be very similar. On this graph, I use a fairly large t because I want to illustrate the point, but it is the approximation of that slope to represent the slope in continuous time that give us this relationship between S and Z minus 1. So you replace every single S by this formula, you end up with a transfer function in Z, which is something you can use for implementation in a digital control system. That's a method number 1. We call it backward difference method. Method number 2 is called bilinear transform method. Okay, in this approach, the equation number 1 here is this: it's 2 divided by the time interval or the sampling interval. Time interval, sampling interval, we use different, sometimes we use different terminologies for the same thing. Okay, and then you multiply this by 1 minus Z minus 1 over 1 plus Z minus 1. Okay, so this equation, if you replace every single S in Ks by this equation, again you end up with a Z transfer function, which is ready for implementation. Now, again, I have a bit of mess here, but the point I'm trying to make here is that this approximation is slightly different from the previous one. The previous one is using a slope. This one, we are actually approximating the cross-section area. Now, the approach here is trying to see that, again, the dotted line is a continuous signal. Okay, the cross-section area between A, B, going through the dotted line to C, and then come to D. That's the cross-section area of xt in continuous time. Again, because I don't know what happens between this point and that point. So I work out the cross-section area between A, B, the straight line, C, and D. Say this is approximately the same as the one from A to B going through the curve C and D. As long as your t is small enough, the difference between the two is can be quite small. Okay, so replace that. Replace every single s with this formula, you end up with a different z transform or different transfer function in discrete time. Then we will be able to implement that controller. Okay, and I will give you some examples in the next session. We take a break, and I'll start talking about examples in a minute.